Okay, first of all, I would like to thanks to Professor Irfanian for the invitation to speak on this wonderful and prestigious conference. And I am really sorry that I couldn't attend this conference physically, even though it's my dream to come to Iran. I hope next time will be possible. I will speak on Ramsey minimal graphs, in particular for a combination of matchings and all graphs. And allow me to share my screen.
Okay, let me start my talk. This is the title of my talk, Ramsey Minimal Graph for Matching. This talk will consist of four sections. First, I will begin with some introduction and then give you some notations that we need in this talk. And then I will explore some known results related to this Ramsey minimal graph. And then in the fourth section, I will derive the necessary and sufficient condition for belong to this Ramsey minimal graph class. And then we characterize all Ramsey minimal graph for certain age. Yeah. Let me start with the introduction. Ramsey theory has been extensively studied since 1928. At the beginning, this problem was studied in mathematical logic context by Frank Planton Ramsey, with the main theme, this order is impossible. These are simple examples. First, it's trivial that from any three persons, there are always two persons with the same gender, right? And then the second examples, from any six persons, there are at least 3% know each other or 3% do not know each other. And the number 6 is the least integer. And the third one, in any ordering of the first 101 positive integers, there are always 11 of them forming an increasing or decreasing sequence. However, if you order the first 100 positive integers in the following way, this one, in this order, then there is no increasing nor decreasing with 11 elements. As you can see here, there are only an increasing or decreasing subsequence with 10 at most elements. Now, Ramsey theory has been generalized in many ways by releasing the completeness, allowing G and H here not necessarily complete graphs, or by allowing multi-colors, not necessarily to use only two colors, but we may use three colors here. And by changing the domain graph, not necessarily to use a complete graph, but we may use a complete multi-parted graph. In this talk, I will focus on Ramsey minimal graph. Now we introduce some notation here. For given graph f, g, and h, what we mean by a g, h coloring on the graph f is a red-blue coloring on the edges of f, where neither a red
G nor a blue edge occur. And what we meant by graph F, a Ramsey G comma H minimal graph, if F satisfies the following two conditions. First, F implies G comma H. That means that in any red-blue coloring on the edges of graph F, there exists a red copy of G or a blue copy of H in F. And the second condition, if you remove any H, E in F, then the first condition will be destroyed. That means F minus E no longer implies G comma H. And the set of all Ramsey G comma H minimal graph we denote by R G comma H. Consider the graph F. Here, we will show that F will imply 2K2, C4. Since if you take any red-blue coloring on F without red 2K2, then all these red edges will be incident to a single vertex, like this. Yeah. If in that case, then you may have a C4 in a blue color. Or incident to this vertex, all the red edges, then in this case, you have a C4 in a blue color. Therefore, in any coloring, you will have either 2K2 in red or C4 in blue. And now, if you remove one edge from F, then we will show that F minus E does not imply 2K2, C4. If you remove an edge here, then I can have a coloring like this, such that no 2K2 in red and C4 in blue. Or if you remove an edge here, you have this kind of coloring. Or if you remove an edge here, then you will have this coloring. Therefore, these two conditions are satisfied, then F belong to Ramsey minimal graph 2K2, C4. Now I give you some known results related to this topic. First, Bohr, Erdős, Fodry, and Self in 1978 proved that if G is a matching and H is an arbitrary graph, then pair G, H is a Ramsey finite. That means the number of non-isomorphic Ramsey minimal graph for this pair is finite. Trivially, if you have K2, H, the set is only having one member, which is H itself, and then 2K2, 2K2, they have a two graph, C5 and 3K2. If you change 2K2 by C3, and then you have K5, 2C3, and G, this graph. Next, this is from Bohr, Erdős, Fodry, and Self, considering 2K2, 3K2, and then 2K2, 4K2. And then by Mangerson and Ockerman, prove that 2K2, K13 consists only one singleton graph. This is 2K13. In general, Burr-Fordry self-edish ratio in 1981 able to characterize all Ramsey 2K2, TK2 minimal graph as follows. It's clear that the Ramsey minimal graph for K2, H is an H itself. However, the determination even for 2K2, H is non-trivial. Of course, T plus 1, K2, is belong to this Ramsey minimal graph. Now, consider the set of Ramsey minimal graph 2K2, TK2, which are not T plus 1, K2. And we have the following theorem. If F is belong to this set, if and only if these three conditions must be satisfied. This is true because when the edges of graph F are two-colored such that no red 2K2 as a subgraph, then the red subgraph must be a triangle or form a star. Now, this result characterizes all Ramsey minimal graphs for 3K2, P3. Yeah, we have this set of disconnected Ramsey minimal graph for this pair, and this set contain all connected graph of this Ramsey minimal graph. Now, in the next section, we derive the necessary and sufficient condition of Ramsey MK2, H minimal graph, and then we determine all Ramsey minimal graphs for MK2, H for some particular graph H. Now, to obtain the necessary and sufficient conditions, we use the following lemma. The graph F has at most T independent edges if and only if the graph F can be decomposed into a subgraph induced by SK. This is a set of K vertices, union of some induced subgraph by outside sets. To prove that, let's suppose N has order N and assume that F be a connected graph. Since for a disconnected graph, we can consider each of its component, and suppose F has at most T independent edges. Therefore, T is less than or equal floor of half N. If T equal floor of half N and out N, then choose S naught as a empty set. In that case, we can have the decomposition like this of F. Now, if T equals half floors and N is even, then choose any singleton vertex set as 1, and we have the following decomposition of F. The third case, if T is less than floor of half N, then set T independent edges in F, say M, which is a set of A1, A2 up to AT, and of course, M is a maximum matching in F. Then define as T the set of like this. Then if all edges of F are in the induced subgraph by ST, then we have this decomposition. Otherwise, suppose to the contrary that F is not equal this decomposition, it means that we have an edge in F such that not in the induced subgraph by ST and also not in the union F. Now define this set, then we will have a matching with the T plus 1 edges, which is a contradiction with the maximum matching M in F. Conversely, we observe that each vertex in SK can be viewed as the center of some star in FSK. So there is at most K independent edges in the induced subgraph by SK. On the other hand, the subgraph induced by outside set of F contain at most I independent edges. Therefore, altogether, we will have T independent edges in F. So that's all the proof of lemma 3.1. To illustrate, consider the graph F having 5 independent edges in pink colors, 1, 2, 3, 4, 5. Then if you choose set S2, consists of V6 and V9, and S7, this set, then we obtain the decomposition of F is like this. We can see here the subgraph induced by S2 in blue color, and then the subgraph by S7 in the brown color. Or we can decompose of F by S3 and S5 like this. Now we come to the main theorem. This theorem gives us the necessary and sufficient condition for Ramsey minimal graph of MK2, H. The proof is as follows. Suppose, to the contrary, that F belong to this Ramsey minimal graph, but for some K subset SK and alpha I out induced subgraph of F, where this one is satisfied, and this graph does not contain H. Now, define a red-blue coloring phi of F as follows. Phi x is blue if the edges in this subgraph, otherwise is red. And notice that the blue subgraph of F does not contain a blue edge. And the red subgraph of F is a subgraph of this decomposition. So the red subgraph contains at most M-1 independent edges. Hence, we obtain a MK2, H coloring of the edges of F. Therefore, this is a contradiction. Conversely, consider any red-blue coloring of edges of F not containing a red MK2. So, either all edges of F are blue, or a red subgraph of F contains at most M-1 independent edges. And by the previous lemma, lemma 3.1, we have the decomposition, all the red edges in F. And by first condition, the blue subgraph FP contain H. Therefore, we have the implication F implies MK2, H. Next, to prove the minimality of F, we color all the edges of F minus E minus SK minus the set of all edges in curly F with blue and the remaining edges with red. And by the second condition, F minus E does not contain H. And by lemma 3.1, F minus E contain at most M minus 1 independent red edges. Therefore, we have F minus E does not imply MK2, H. Then we conclude that F is a Ramsey minimal graph MK2, H. So this is the end of the proof. Even though we already derived the necessary and sufficient conditions, but finding all Ramsey minimal graph of MK2, H is still a difficult problem. But if we fix graph H, then the situation might be different. Now consider if H is a P3, then we have the following necessary condition by Mushi and myself in 2012. And furthermore, if F is a Ramsey minimal graph of 3K2, P3, then F minus any vertex imply 2K2, P3. And the second one, F minus the edges of triangle implies 2K2, P3. Furthermore, we have these two theorems for disconnected graph, for a Ramsey minimal graph of 3K2, P3. And if we consider the result of Mangerson and Ockerman about the Ramsey minimal graph of 2K2, P3, then we can show that the only disconnected graph in Ramsey 3K2, P3 are C4 union P3, C5 union P3, and 3 P3. Furthermore, for connected ones, trees are not possible, and cycles are only C7 and C8. And the circumference is at least 3 and at most 8. But no graph of circumference 3, 4, or 5. And for circumference 6, we have 5 graph pictures in this figure. Therefore, these are all the connected Ramsey 3K2, P3 minimal graph. Now, we could also characterize all Ramsey minimal graph for 2K2, K4. These are all the Ramsey 2K2, C4 minimal graph. And these are for 3K2, K3. Now we could also derive the necessary and sufficient condition for all unicyclic Ramsey minimal graph of MK2, P4. And this theorem give us the necessary and sufficient condition for the unicyclic with P2 pendants. And then the following theorems give us the necessary and sufficient condition for unicyclic Ramsey minimal graph with P3 pendants. And this is the last theorem regarding the unicyclic Ramsey minimal graph with mixed pendant, either P2 and P3. In the last results is related with the subdivision of Ramsey minimal graph for MK2, P4. And these methods can be used to obtain a new Ramsey minimal graph from known Ramsey minimal graph by subdivision 1h 4 times. So I conclude my talk by saying thank you very much dan terima kasih.